Hi, my name is Joshua Edgecombe, and today I'll be talking about how computer architecture can be applied to an FPGA. There are three core components to computer architecture: the processing system, memory, and I/O. The processing system can be any unit, module, or component which processes data. In modern systems, this will generally be either a microcontroller or microprocessor, but could also be an FPGA, or a module within an FPGA. The memory can be any unit, module, or component which stores data. Generally, memory is broken down into, at the very least, three tiers. In the first tier, we have a relatively fast and small capacity storage which provides immediately accessible data and instructions to the processing system. In modern computer systems, this is generally the cache on the CPU. In the second tier, we have an intermediate speed and capacity storage which acts as a stepping stone between immediately accessible data for the CPU and long-term storage. This tier is generally orders of magnitude faster than the long-term non-volatile storage, but is too slow to provide data to the processing system continuously. In modern computer systems, this would be the place for RAM. In the third tier, we have the relatively slow and large capacity storage that is used for long-term storage and is inherently non-volatile. In modern-day computer systems, this will be the hard disk, flash drives, and other external media such as CDs, DVDs, and Blu-ray discs. I/O, or input and output as it stands for, can be any unit, module, or component which sends or receives data. There are many standardized communication interfaces such as USB, SATA, and PCI, which allow the processing system to communicate with other systems or provide information to the end user. Gpio, which stands for General Purpose Input and Output, is generally used to communicate between custom digital hardware. So if we take a look at this visually, we can see how the core components are connected. While connections exist between the processing system and external communication, or I/O, as well as the processing system and memory, there is not inherently a connection between the memory and external communication components. When this connection does exist, it is referred to as DMA, or direct memory access, because it directly connects external ports to memory without requiring the consistent attention of the processing system. With that being said, it is generally not a true direct connection without interaction from any processing system. What do I mean by that? Well, DMA is generally performed by a coprocessor or peripheral subsystem. So while the DMA can be seen as a separate connection that exists directly between external communication and memory, it generally requires a coprocessor, which behaves as another processing system, to facilitate the transfer of information between the two core components of memory and external communication. So with our knowledge of computer architecture and how these core components connect and interact, how do we apply that to an FPGA? For example, if we wanted to create a computer system with a processing system, memory, and I/O on an FPGA, can we do that? And if so, how? Well, we have a few problems we need to address first. Like, how do we translate some of these core components to an FPGA? And how do we connect them together inside the FPGA? Let's take a look at the processing system first. The two main methods of implementing a processing system on an FPGA are by using a soft core processor or a hard core processor. A soft core processor is a solely software-defined processor. Now this is not software as is commonly understood. This is RTL, or register transfer logic, defined using an HDL, or hardware descriptive language, that defines how the processor functions. A soft-core processor is not inherently separate on the FPGA's silicon from other custom logic. With that being said, it behaves as a separate entity within the FPGA, with regards to the other modules defined on the FPGA. A hardcore processor is a separate piece of silicon within the FPGA, which behaves as an independent processing system. A hardcore processor's silicon cannot be reallocated to be used for other functionality or other modules within the FPGA. Its sole purpose is to act as a processing system, and the exclusion of the hardcore processor in an FPGA doesn't reduce the custom logic resource utilization within the FPGA. Storage within an FPGA is generally handled in one of three ways. The first and most commonly used form of storage in FPGAs is the flip-flop. Flip-flops, also known as registers in FPGAs, can be used to store relatively small amounts of data that is immediately accessible to custom logic written in an FPGA. While they can be defined to be addressable, they are not inherently addressable. The second common form of storage in an FPGA is BRAM, which stands for block RAM and is an FPGA primitive. An FPGA primitive is an HDL object that corresponds to a physical portion of silicon within the FPGA. BRAM can be used for large amounts of addressable data that can be non-sequentially written to and read from memory, but only one word at a time. The word length for BRAM can be varied depending on the FPGA used, where word lengths greater than 512 bits are not unheard of. Greater word lengths can be achieved by using multiple BRAMs simultaneously in parallel. This can allow for substantial amounts of data to be concurrently written to and read from memory. BRAMs also find a common use case in clock domain crossing FIFOs, which allow data to be safely transferred between two portions of logic driven by separate clocks within an FPGA. BRAM most closely represents RAM in modern computing systems. Another key feature of BRAM is that it allows for multiple independent read and write ports. The availability of this feature, however, is dependent on the FPGA being used. The third form of storage commonly used by FPGAs is external memory. External memory is often used when the FPGA resources are constrained by the logic being defined on it or when non-volatile storage is required. When external memory is necessary, it is achieved through external communication and control lines. External memory can be any common form of memory and can be either volatile, such as DDR memory, or non-volatile, such as EEPROM. External communication on an FPGA is generally achieved through the use of modules written for the FPGA that connect the custom logic defined on the FPGA to communication standards such as USB, SATA, or PCI. Due to the prevalence of communication between devices in modern-day technology, there are often modules written by other developers called IP cores that allow you to connect your custom logic to other devices using those common communication standards without having to write the HDL code yourself. So, how do we connect our custom logic, processing system, and communication IP cores together in a way that allows them to all easily communicate? Standards. The most common communication standards used in modern FPGAs are the ARM AMBA, which stands for Advanced Microcontroller Bus Architecture, communication standards. While the ARM AMBA communication standards define many protocols, some of the more commonly used protocols are Axi, APB, and ACE. While IP cores would ideally be portable between different chips and even different manufacturers, different FPGA manufacturers tend to have IP core ecosystems specific to their chips and prefer certain communication protocols over others. For example, Xilinx and Intel, formerly Altera, generally prefer Axi, while Microsemi prefers APB on some of their more resource-constrained FPGAs. Let's take a look at what our final implementation looks like with the processing system, memory, and I/O. We have a soft-core processor which connects to a local memory bus controller. The local memory bus controller provides the processor a memory space with instructions and data that are immediately accessible and can be continuously fed to the processing system's pipeline. This piece provides the functionality of a cache on a modern CPU. In order to connect our pieces together, the Axi Communication standard will be used. Axi is a master-slave communication interface and treats the slave as an addressable memory space with reads and writes being performed to the appropriate addresses on the slave device or module by the master. The Axi interconnect allows multiple masters to connect to multiple slaves simultaneously. This converts the address space provided by a single Axi slave module into being part of a larger address space provided to the processor. In the next video, we will walk through how to implement this system on a Xilinx Zinc 7000 FPGA using the Digilent PINC-Z1 development board. Thank you for watching.